Seminars stream live on the first Thursday of every month at 11 a.m. Eastern. They're also available to watch anytime on the YouTube channel. Also on YouTube, we have all our previous speakers as a part of the seminar series, and I encourage you to check them out. We also have some excellent speakers planned for the upcoming months, and we hope that you will join us for all of them. Before we get started, a few quick thank yous. First, Dr. James Batias, the Center's Director, Jennifer Baltic, the Center's Administrative Coordinator, and two CMCC students without whom the seminar would not happen, Katie Floyd and Ryan Kwok. Please do continue to follow us on our YouTube channel at CMCC Mechanochemistry Discussions. Before we get started, a few quick guidelines. A little bit differently than usual, this seminar has been pre-recorded because of the large time difference between the US and Korea. Because of that, if you have any questions, please forward them to cmccdiscussions@gmail.com, and we'll propagate these questions to the speaker, who promised to answer them the next day. So, without further ado, it is my pleasure to welcome today's speaker, Dr. Yung Kim. Yung Kim is an associate professor of chemistry at Yongbuk National University, leading the organic and polymer synthesis group since 2015. He was trained at KAIST, where he received a bachelor's degree in 2001, and the University of Pennsylvania, where he received his PhD in 2005. He was also mentored by Professor Patrick J. Walsh, and he gathered experience at Cornell University and IBS under Professor Geoffrey W. Coles and Professor Subbok Chang, respectively. His expertise spans organic and polymer synthesis with a focus on mechanochemistry, post-polymerization, modifications, and chemical recycling of plastic. It is my pleasure to welcome Dr. Kim to Mechanochemistry Discussions.
So it's my great honor to have an opportunity to speak about my chemistry and mechanochemistry to this great audience over the internet. I know the CMCC have been fantastic group of people together, and then they're spreading this mechanochemistry to the chemistry world, and I'm really happy to be a part of this wonderful community. And then today I will talk about some research. Our research group have been done about 7 or 8 years, and then the title is Mechanochemistry on the Opportunity for Polymer Synthesis and Chemical Recycling. My name is Jeung Kim. I'm an associate professor at Jeonbuk National University of South Korea. So to begin the mechanochemistry seminar, I would like to share or introduce my research group. So our research group is having background on organic chemistry. I'm originally transferred to polymer synthesis, and thus we have a strong background in organic reactions. And based on the knowledge, we're trying to make a big molecule that's a polymer. So majority of research we're doing is in mechanochemistry, which we utilize in ball milling machine to making polymer. At the same time, we're also doing some solution chemistry mostly. Here is called a post-polymerization modification to make functional polymers an easy way. And then this is a kind of recent interest to everyone is a plastic recycling. So using a chemistry tool, we want to depolymerize in polymer to this raw material monomer. That's another important research topic is ongoing currently in our group. And then one of the topic I will discuss this one together is called the mechanochemical plastic recycling at the later part of this presentation. So let's begin some mechanochemistry talks. And I'm sure maybe not everyone, but many of the listeners or attended together today may have experience about the mechanochemistry, may heard of mechanochemistry through previous presentations. So I'm not going to spend too much time on the mechanochemistry, but I will spend some time narrowing down to polymer mechanochemistry. So the mechanochemistry is about the research area we utilizing mechanical force to make or break a chemical bond and utilizing for chemical synthesis. When we go to the polymer mechanochemistry, that's actually divided into two different areas. So left part, I just said the bond breakage for polymer synthesis. So polymer or plastic have been used long time in our lifetime, and we already, over 100 years, we already know that when we apply the external force to polymeric material, chain breaking event would happen. So under the force, molecular weight goes down, viscosity goes down, and mechanical strength goes down. So it used to be a kind of bad event for performance-wise. But smart chemists over a long time utilizing this phenomena to making some smarter materials. And top example is showing one great example that here is a highly strained triangle cyclopropanes in the polymer backbone. When we apply the force in opposite direction, it could break one of these carbon bonds, and then it will generating this new type of polymers. Probably it's hard to make or impossible using general polymerization techniques. So this type of the smart application have been used, and recently the Ito group in Hokkaido utilizing even this breaking event. So in the generic polymer, we apply the force and breaking it, generating macroradicals. And this macroradical coupling with this functional molecule, after combining these two molecules, they're generating highly fluorescent polymers. Again, is another harder one to make through general polymerization. So this type of smart research on utilizing the chemical breaking event has been a major theme in polymer mechanochemistry. However, our research group taking different route. Our group is kind of more fundamental way. So we would like to using this ball milling technique to synthesize polymer from monomers. So, I mean, the polymer, a lot of them we are using that way in the solution chemistry, but by applying mechanochemistry, first merit we can expect is the solvent-free reaction. Thus, in terms of green chemistry, we can do green solvent-free polymerization, which is highly beneficial for our process. At the same time, when we using this type of unique process, sometimes we are able to make mechano-only structures. Again, some polymers, which is very hard to make using conventional solvent technique, we are able to make using mechanochemistry. And I will discuss both things today in the polymer synthesis. As I mentioned, polymer mechanochemistry mostly focused on chain breaking event. And constructive polymer mechanochemistry, which begins with monomer, is minor area, but has a long history. So I want to summarize it. What kind of things have been done in this area, making polymers using ball milling? So as I said, around 100 years ago, Hermann Staudinger already described that external force can break down polymer chains here. However, 1959, the first mechanochemical polymerization of binary monomers was reported by Russian chemist Kargin. And after that, it has been forgotten. But in the 80s, one of the very famous Romanian chemist, Simeonescu, continued this research on vinyl polymerization using ball milling chemistry. And these two groups already discovered that with the proper mechanical force, we can polymerize this vinyl type monomer into polymers. However, thinking about the 50s, 60s, 70s, or early 80s, the limitation of analysis method gave us not clear image about event. In 1990s, one research group in Japan, led by Kujuya, they revisited this area with modern techniques. Same machine we're using currently, like NMR, EPR, IR, or GPC, many techniques, they applied it now we are able to understand exactly what is going on when we ball milling these vinyl monomers. So we now have fundamentals about this event. And then this research is mostly solely conducted by this group. But after 2000, this is kind of green chemistry time. So people realizing it, we need to improve our previous chemical synthesis, adapting green chemistry ideas. And then obviously one of the major movement was solvent-free chemistry. In 2010, several research groups started building up some polymer synthesis, focusing on solvent-free chemistry. And then now we're realizing it, there is more than that. Now several research groups working on together in this area, and we are making significant progress year by year. So today, based on our research topic or research experience, I would like to address some issues we encountered and how we answer. So research group, our research group having worked on the mostly chain polymerizations using some catalyst, initiator, and monomer, and trying to making a high molecular weight polymer with controlled dispersity. I mean, we developed several examples, and I went to some conferences and talks. And then the one question I'm always getting was about the curiosity about the mechanical force. Does mechanical power matter? Really? Can it control the chemical reactions like a temperature? So here's the example I want to show in the left, our first paper published in 2017 about the ring opening polymerization of lactite using organocatalyst DBU. This is an entry I tried to optimize the mechanical power using different type of balls. We used the stainless balls at the time, and then here's the container has a different types of balls or different number of balls. So when we trying to small balls here, 7 millimeter diameter, and then when we adding one ball, two balls, three balls, there's a slight difference in conversion. So, I mean, in this time, we believe that number of balls was not super important. However, when we changing the ball from 7 to 12, so we're using a bigger ball, and there's a significant improvement in conversion. Let's compare the number 4 and number 5 entry, number 4 and 5. Number 4 and 5, 4 has the 7 millimeter balls, 5 has a 12 millimeter balls. If you put those two into the balance, total mass of one ball 12, 5 balls of 7 millimeter is about same. That means in the container, overall mass were identical. The difference is in the 7 millimeter balls, there will be more frequent but weak collision. And entry 5, 12 millimeter ball, that will be making a big impact per collision, but the frequency of collision will be smaller than previous number 4. But as we see here, bigger ball gave us much higher conversion in the same conditions. So in this example, what I observed was there is some impact power is control the reaction. Weak the collision delivering low energy, and we believe high impact collision delivering higher energy to the system. But this one gives about that mechanical power can control the reactivity. And similar observation was we again made using the ramp chemistry, the Grab's catalyst in the polymerization of the norbornene group, ring opening polymerization. We also observed a similar event. High mass 10 millimeter ball gave us very high conversion, while smaller ball gave us lower conversion. So we believe that, so if you look at the previous many mechanochemistry paper, there's some difference examples. Sometimes the number of balls making a more impact. Sometimes the mass of the ball making a more significant impact, maybe little by little, but just in our observation, we would like to claim that mechanical power here impact magnitude could control the kinetics. And second issue is something very unique to polymer chemistry. Like a normal organic synthesis, this part doesn't apply, but only polymer chemistry happen is the chain breaking event. So at the beginning of polymer mechanochemistry, I already mentioned that when we applied external force to polymers, chain will break down. So in our observation of organocatalyzed ring opening polymerization of lactide, at the initial stage about 1 hour, here is solid line, we had around 30% conversion, and up to 1 hour, molecular weight followed. So as the reaction goes on, tail will get longer. So this is kind of expected phenomenon of chain polymerization. As the reaction goes further, 2 hour, 3 hour, 4 hours, you can see conversion keep going on. However, molecular weight failed to follow the trend of conversion. Obviously, when we consume more monomer, it will be proportional to molecular weight and conversion both should have a proportional relationship. But this molecular failed to follow the conversion, which happened again in the ring opening metastatic polymerization. This is a green line, the conversion line. Very quickly, in a 60 minutes, in an hour, reaction goes to complete conversion. However, molecular weight didn't follow that. Molecular weight was highest at the early stage, 10 minutes, and after that, gradual decrease was observed. What it implied is that at the initial stage, we grow the kind of short chains. But after significant conversion, maybe after 20%, 30%, we have decent size of polymers, long polymers. And those long polymers start to degrade upon external force. That means this area or this area, chain growth and chain destruction happen at the same time. So to control one of the important things in polymerization is about the molecular weight control. In the solution chemistry, we only need to thinking about the chain growth kinetics. However, chain breaking is happen together here. There's external kinetics happen in solid state chemistry, and we need to thinking about how can you selectively reduce chain destruction over chain growth. After some research, we found that liquid assisted grinding can solve this problem. So we made this observation in both lactide case and the ring opening metastatic polymerization case, but I will only bring up here one example is a metastatic case. So number one entry is just a simple polymerization I just showed before. Here, number one, chain growth and chain degradation happen at once. After 30 minutes, we got a 90% conversion and molecular weight about 22 kilogram per mole. If we apply same scales in the solution chemistry, which is entry 5, we obtained 99% conversion and then about a double molecular weight. The right scheme is called the GPC, gel permeation chromatography. So this is showing the molecular weight distribution. In the short evolution volume, this means it's a high molecular weight. When this one goes to right side, it means low molecular weight. Let's compare entry 1 and 5 first. Entry 1 is a blue line. Entry 5 is a green line. As you can see, the blue line has the higher population on the low molecular weight side. And also, this is the maximum peak of the molecular weight, and you can see maximum peak even shifted to right side. This means during the mechanochemical solid state ring opening metastatic polymerization, significant chain degradation happen, which shift overall weight to the right side. Thus, we got the lower molecular weight. In the number average molecular weight, weight average molecular weight, both we got a low numbers. And then we try some liquid assist grinding. So adding a very small amount of liquid to the polymerization, and we found a very significant effect. When we adding a 20 microliter toluene to the 50 milligrams of monomer solid state. And we found was by number actually pretty similar with without toluene. But if you look at the graph, it's significantly different. So solution phase again the solid state is blue, and then toluene is red. If you compare blue and red data, red one has significantly higher population on left side. That means toluene successfully protected high molecular weight polymers against their degradation. And then low molecular weight polymer is not coming from high molecular weight. It may be coming from some different kinetics. Thus, we tried using a different types of liquid. And then when we apply the dichloroethane, number 4, it has an almost identical distribution to the solution chemistry. Here, solution is green, and then this dashed line is a DCE in only small amount of liquid to monomers, solid state, and as you can see, it shows almost identical molecular weight distributions. Thus, we believe that when we encounter chain degradation during polymerization, just adding small amount of liquid could selectively slow down this chain degradation while maintaining chain growth mechanism. At this moment, we do not know the vivid answer for this one. We try to understand this system in some several experimentally or theoretically, but we haven't got found yet about the vivid answer, but we can propose some possibility. So our first hypothesis was a lubrication effect. The chain breaking of polymer from the outer force coming from the frustrated situation. So in the solid state, polymer chains got entangled together. And when we applied outer force, the molecules are supposed to move. However, due to the constrained situation, this chain cannot move independently. Thus, chain breaking could happen by accumulating high energy. However, if you're adding a lubricant, so that means chain to chain slippage could happen, chain move around. Thus, upon chain moving around, energy from outer force could be dissipated over the system, and then maybe chain breaking can be reduced. Or other theory we having was a free space. It's same as about the movement. When chains were tightly packed, even they want to move, there was no room to move around. However, by inserting some small molecules into polymer matrix, and the small molecule create some volumes, and throughout that volume, polymer chain could move around upon outer force. So one of them, we believe, is the reason we can protect the polymer from chain degradation. So by having that techniques, previously, we failed to grow high molecular weight because of chain degradation. This trend is supposed to follow. However, adding a toluene into the lactide polymerization, we were able to get continuous of gross molecular weight. That means we successfully prevented chain degradation. And say observation happen again ramp. So previously early stage high molecular weight, later we observed chain degradation. However, when we adding DCE, we are able to getting a high molecular weight chain growth only, and then almost no vivid chain degradation was monitored. So now, using this mechanochemistry, we are able to control molecular weight. This technique is not universal. Some polymerization, this LAG technique is efficient. Some polymerization is not efficient. When I'm saying not efficient, means maybe we didn't try enough. But if you find a good solvent or good LAG system, maybe we are able to grow the chain further and further. This concept have been applied to different types of techniques by other research group. And Pang in 2023 reported atom transfer radical polymerization, as you can see, continuous growth of polymer, and then with a low dispersity and successful using ATRP in the bone milling. At the same time, the Golder group, he presented the CMC seminar a couple of events ago, and maybe he explained it, but his group in Washington, they also developed the reversible addition fragmentation chain transfer polymerization, also grow the chain with the molecular weight control and their low dispersity. And another question is about the rate. So commonly, in many examples, mechanochemistry often observing high rate acceleration comparing to solution system. If you go to the kinetic equations, we have a kinetic constant and then concentration of each reactant. And then we're using the equations for the understanding the rate. Imagine you doing a mechanochemistry without solvent. That means we could conduct chemical reaction at the theoretically maximum concentrations. That means if you're making a good mixing, we're supposed to have very fast rate because of concentration effect. So in 2014, the Swagger group reported one elegant example. It's a Gilchik polymerization. They are synthesizing this conducting polymer PPV using a bone milling with a potassium T-butoxide. In the solution chemistry, it's really long reactions. Sometimes takes more than a day to making a good size of polymers. However, when they polymerized it, even after 10 minutes, they were able to get significant amount of polymers. So this one showing that some reaction which require about a day could be done in a minute scale. We observed similar situation when polymerizing trimethylene carbonate monomer with their organocatalyst DBU. In this solution chemistry, methylene chloride, we only got the 3% conversion in 1 hour, 43% conversion in 24 hours. However, when you apply this one, just transferring to bone milling and removing methylene chloride, solid state, we received 75% conversion in 1 hour, almost full conversion in 2 hours. So this one showing that mechanochemistry is a one tool to enhance the reactivity. So whenever you're having some trouble because of low reactivity or lower rate of polymerization, mechanochemistry is a system used to try. And this section is I will discuss about dispersity. So in the polymer chemistry, in polymer synthesis, so when you're making a polymer, it's not a single chain. So we have a lot of polymer with different chain lengths, and we just we got the average value out of it. So sometimes, depends on technique, sometimes you could be making a lot of polymer with a similar chain lengths in situation we call the low dispersity. However, sometimes we got a very broad range of polymer chain lengths, very short to very long. It's a wide range of polymer lengths. We call the high dispersity. And then controlling of dispersity is very important especially for specific bio applications. So many polymer chemists try to synthesize polymer with a very low dispersity. So in case of chain polymerization, we need to thinking about two different events, which we call the initiation and propagation. Here we call the kinetics of initiation called Ki, or rate of propagation we call the Kp. So to obtain narrow dispersity, what we need to have is very fast initiation and very slow propagation. If we got the reverse situation, very low initiation, the slow initiation, but fast propagation, we're supposed to get the broad dispersity. So let's talk about the only first system here. So we have two system has the two different catalysts, identical, but the top one has the DBU catalyst, bottom one has TBD catalyst. And then TBD catalyst known for the fast synthesis, and DBU known for the not super slow, but compared to TBD is significantly slow. And initiation is the event about the mixing. So first initiator meeting to the first monomer, that's what we call the initiation. When we mixing this number 1, number 2, number 3 reagent in the ball milling, we encounter unique situation, heterogeneously dispersed situation. And upon initial grinding, we have some mixing time of these 1, 2, 3 molecules into the system, so we need the time to do it. However, in the solution chemistry, we just making a complete dispersed homogeneous situation at the beginning of the reaction. So that's the difference. In the solution reaction, both DBU, TBD known for very narrow dispersity. However, in case of DBU, maybe this first mixing event only require a couple seconds or less than a minute. Thus, comparing to whole propagation time, our initiation is really fast. It's kind of second. First mixing is a second scale, overall propagation in minute scale. Thus, this situation, high initiation rate, but slow propagation. Thus, we are able to get a low dispersity. But in case of TBD, it only happened 5 minutes. Thus, our initiation rate become very significant compared to propagation. Thus, it's approaching to this bottom case. And then we receive the broad dispersity 2.00. Why I'm bringing up this example is many times ball milling chemists or some other people asking me about that, how you're transporting solution reaction to the solution, the solid state chemistry. Just the polymerization may be same, but the kinetic get disturbed. Most of the information we learned from solution chemistry is valid, but sometimes not. This is one example. Especially initiation, in the solution chemistry, we began the reaction at the homogeneous state. But in case of this ball milling chemistry, inherently it has a delay in mixing, which causes delay in initiation. So this delayed initiation could make an impact on dispersity. So very careful choosing of reaction condition is required if you want to control the reactivity at the same time dispersity. Similar observation was made in the ring opening method, that is fast catalyst G3 showed a broader dispersity and slow catalyst G1 at 30 minutes, only 20%, but the compensating slow reaction, we received narrower dispersity. And then we are currently trying to making some more clear explanation about this one in our research group. And then also, I want to show us that in case of dispersity, so this is one equation. Usually you can learn in the polymer chemistry class about the dispersity from the living polymerization. And then this Krabs catalyst chemistry on the ramp is one of the well-known example of living polymerization. So as the reaction goes on, dispersity is supposed to getting smaller, smaller, smaller. And then this one, at the lower conversion, at the higher conversion, you can see dispersity goes down. And then this one is also showing that this ramp technique following living polymerization character. But they're not always following the same process. So this is one example we reported in 2023. We tried to develop the anionic polymerization in the solid state. This anionic polymerization in solution have been known for harsh reaction conditions, very low temperature, and very, very rigorously purified monomers and initiators was required. We tried that maybe we can overcome those kind of the drawbacks in the solid state chemistry. First, we just started it, mixing these two, and then we received the polymer. We were excited that maybe we developed the ball milling anionic chemistry. However, when you're analyzing the kinetics, it was not. Again, as the blue one is the conversion, and then the orange line is a molecular weight. We observed a similar trend in the ramp, or the ring opening polymerization of lactide. So there is obvious chain breaking event. What is the mean is, at the very early stage, before degradation, all these polymers at the low conversion was produced solely by anionic chemistry. It's beautiful. However, after certain chain length, chain breaking happen. That means at the each chain breaking, there will be two radical formation happen. Now we have two different types of reactive chain end. One is anion, two is a radical. If you see the kinetics, the rate, at the initial stage, reaction is very slow. It looks like a induction period, and middle time there is a high rate observation, very sharp monomer consumption happen. What it means is, at the early stage, only small number of anion consume the monomers. So slow kinetics, anion polymerization. But after a certain time, because of the chain breaking, now we have more radicals and more radicals and more radicals. Here, now we have more radicals than anions. Thus, in the middle of time, we believe that radical polymerization was the main event. So this scheme shows that at the early step is anion initiation. However, after mechanical degradation, it becomes radical propagation, and then chain degradation happen together. So this kind of continuous loop happen throughout the whole process. So the lesson I want to deliver here again is, so if you go back to polymer chemistry class and chain polymerization, there is a three major types of reaction happen at once, which is initiation, propagation, and termination. However, there was a one mechano-only event is a chain scission. So to control the whole chemistry in mechanochemistry polymerization, we need to balance four different chemical reactions presented here, while only three reactions was happening in solution. So it's, I say, more complicated. And previously, I showed that if we choose light liquid assisted grinding, we can minimize this chain scission event. So this one gives the idea that, when we transfer reaction to mechanochemistry, it is more complicated. And now I'm gonna move to some general questions. I mean, this is kind of question maybe you already saw in the previous seminars about the temperature. Many mechanochemists or non-mechanochemists has an idea about that. Mechanochemistry is actually about thermal event, not a kinetic event. Kinetic collision, believe that causing very high temperature at the collision spot. Sometimes people say like 100 degrees or 1,000 degrees, or like plasma system or magma system. many names on that. But over the time, now I believe maybe it's not. And two shows that we adapt one organic reactions, which is involving acyl azide. Acyl azide is highly sensitive to temperature. This nitro benzyl acyl azide known to rearrange to this isocyanate around 50 Celsius degree. So if we increase temperature around 50, it quickly rearranges to this isocyanate. If this ball milling is a highly temperature related event, this rearrangement should happen immediately. However, when we grinding the solid material with ball mill in the Teflon jar or stainless bowl, we only observed less than 1% conversion to 2. We increase the energy to the zirconia, higher density material, or stainless steel. Still, this rearrangement to 2 is a very minor event. Thinking about if this is thermal process, this rearrangement should be very fast. However, we only observed very low conversion to 2. So we believe that it is not thermal event at the collision point. Also, one of the things we can imagine is, so using a different force, not a temperature event, maybe we can apply the more energy than thermal 50 degree. Previous research on this reagent, every reaction is supposed to run below 50 to prevent rearrangement. However, mechanochemistry can do some more energy supply while maintaining low temperature. Thus, in this publication, we are able to get the CH amination reaction with a higher level of reactivity than thermal because we deliver the kinetic energy is a high energy without increasing temperature. So this one, so also many research groups in the community, we believe that temperature is not a major effect on this chemistry, and then more evidence building up in this area. And then about the final chapter of this talk, and I will discuss about the miscibility. This is one of my favorite quotes I got from the late Professor Petrosky of the Iowa State. He said, you can get complete dispersion, something that would be very difficult to achieve by melting the two components together. So if you have two reagents which are immiscible, like water and oil, even you shaking it, if it has a mobility as a liquid, they can be separated. Phase separation would happen. However, if this is solid, once you disperse it, and it's kind of frozen because of the material would not have no mobility. And this one gave me some idea about maybe this unique situation of the solid state could give us new chance for polymer synthesis. So it's not surprising that the solubility issue is not very different from the solution state. Like Professor Ito, 2021, they developed the Suzuki coupling reaction involving almost insoluble in any solvent. And then this kind of pigment undergoes this Suzuki coupling reaction. They got this molecule. Again, in the solution, this molecule has extremely low solubility, and conducting this reaction in the solution was impossible. Borchardt group in Bochum, Germany, published one paper 2018. They made a small nanosheet graphene. Again, thinking about solubility of this material, from this starting material to here, if you're conducting solution state chemistry, early precipitation would happen, and then mostly you will get a partial reaction. However, under the ball milling chemistry, we are able to push the reaction all the way to the end, generating this gigantic nano sheet. So I want to adapt this idea to the polymer chemistry, especially for polymer science. copolymerizing highly hydrophilic ionic material with highly hydrophobic this type of organic material, putting these two into the one polymer chain has been challenging. But using a ball milling, maybe we are able to overcome this limitation. So first example was the ionic monomer polymerization. So the same norbornene here, but here we have an ionic component. Thus, these two ionic monomers only soluble in highly polar media like water. When previously research group tried to polymerize this one, however, normal Grubbs catalyst is a hydrophobic, so these two monomer and initiator are immiscible or hard to find co-solvent. Thus, people developed the modification on their backbone generating ionic unit. Now, this water-soluble metathesis initiator can react with this ionic monomer in the same phase and get the polymers. However, in the mechanochemistry, we are able to just mixing these two and just grinding. And then after 30 minutes, we received quantitative conversion to high molecular weight ionic polymer. We added a very small amount of water or sometimes DMF. We believe that this is highly required because when this monomer form the solid, it's kind of the ionic cluster. And then this cluster energy is too high. So we believe this small amount of water alleviating molecule to molecule interaction, thus mechanical force could do some molecular movement. That's our hypothesis about that. And using this movement, under this movement, this immiscible catalyst or initiator can enter into this system efficiently and then produce desired polymer with a high efficiency. We continue this reaction on other system. So hydrophobic monomer, hydrophilic monomer together, copolymerizing. Again, copolymerizing A and B in the solution system, we need to find the solvent system, which is solubilize A and B both in the one system. However, very hard to find it. But in that case, don't worry about it. Just grinding solid state A, solid state B, and just grinding and a copolymer throughout the whole different ratio of hydrophobic, hydrophilic monomer. We got the near quantitative conversion after 30 minutes and then similar molecular weight. After this experiment, we encounter one question. What type of structure will we synthesize throughout the reaction? For example, the G3 catalyst and monomer A and monomer B can mixed. If these A and B are separately added as a powder, we have a powder A and powder B. Maybe powder A and B independently existing. And if G3 goes to powder A, there is a predominant A, thus we will generating polymer A only. If the G3 goes to powder B, we predominantly will get a polymer B. Thus, in that case, maybe we can anticipate this block type structure. If this A and B mixing was super efficient, we could expect that molecular level mixing would happen between two immiscible monomers, and we could get a random distribution. And to prove the structure of that, we conducted thermal measurement, is a DSC measurement. So using DSC, we are able to get a glass transition temperature of each polymers. So previously I said if we got the block polymers, that means we have a block A and block B. Each block would have their own glass transition. And there should be distinctive two different shift about their phase. However, throughout the whole system, we only received one transition. So this implies that maybe we got the random structure. At the same time, when we got the pure polymer 1, their glass transition temperature is around 116. When you get the pure ionic one, we're supposed to get 170. And then by varying their ratio, this temperature actually dictating their ratio. When you have a higher hydrophobic content, transition temperature is low. As we increase the higher ionic content, glass transition temperature increase gradually to here. And this is another evidence that we achieved very thorough dispersion of ionic and hydrophobic two monomers into the molecular level. And then we got the random polymerization, again, which was almost impossible in solution chemistry. So recently, we just submitted this one to the one journals, and we want to show that it's a kind of exotic examples. So here is a 99% of the ionic monomer with very, very hydrophobic porphyrin monomer together, 1%. And then we obtained ionic polymer. And then this ionic polymer showing unique porphyrin patterns in the water. So as you can see here, this is a blue color is the UV absorption of the water solution. However, when you're shifting to organic solvent, here you can see clearly why precipitation is precipitating whole polymers, which also remove the porphyrin molecule in the system. So we made a water-soluble porphyrin. Again, it's independently impossible, but very easily we could generating some water solubility of porphyrin into the solution here. And we observed a similar event with the radical chemistry, so sodium acrylate and it's the pyrene and copolymerized together with the cross-linker, we generating a kind of the hydrogel. And then in the hydrogel, because we copolymerize it with the majority of the ionic component and the small organic component, this whole component become kind of water absorption property. So here left, when we have a pure water system, we could see strong signal of the pyrene upon UV radiation. But when we go to the organic solvent, it's completely gone in THF. So this kind of thing, again, we exemplifies that mechanochemistry can offer very unusual combination of the polymer synthesis. Another one is called the post-polymerization modification. So like a highly hydrophobic polymer could react with ionic compound and then generating good conversion to imine or reverse way. Sorry about this, hydrophilic polymer react with a hydrophobic reagent and then reaction is very quickly happen. When you apply this reaction in the solution system, reaction was very slow or never reached the completion. So this one also showing is that the merit of mechanochemistry. Don't think about the solubility, just you can proceed it. And then this is the final discussion of today is chemical degradation. I mean, plastic crisis is hit every community, and then chemistry area also because we are the one synthesize the polymer, and they're kind of the guilty about that. I mean, we made our life very easy by using plastics, but certainly society asking us that you made a polymer, that means you can degrade the polymer. So chemical recycling is the degradation to monomer. It's been a very hot topic in the chemistry. And then in the discussion here, I want to say that mechanochemistry can make a huge progress in that area. So the material I'm showing in this slide is a bisphenol A polycarbonate, which is abundant material in everywhere, like a safety glass or headlight cover or compact disc, so many or construction materials and so many areas we utilizing this polycarbonate BPA-based polycarbonate. And once using it, obviously we want to depolymerize it and recover the monomer. So instead of being waste, if you can recover this monomer, we can resynthesizing it. So we can making an infinite polymerization, depolymerization cycle. So we can making a new polymer without wasting materials. That's kind of the ideal way to treating plastic waste called chemical recycling. So this BPA-PC depolymerization one of the best example is methanolysis. So trans-acidification or trans-carbonation, this methanol can breaking down this ester unit and generating free bisphenol A and then getting a dimethyl carbonate, and both material can be treated again to repolymerize. The issue is to react methanol. Maybe we want to have this bisphenol A, PC, and then methanol just mixing it in the solution. Nothing happened. Bisphenol A, PC has no solubility at all in methanol. When you increase temperature to 100 degrees, nothing has happened. Maybe you need to increase the very near critical temperature, high energy, 200 degrees. Some degradation happened, but the reaction was not clean. Interestingly, when we apply just a mixture of this PC polycarbonate and methanol in the bone milling, after certain hours, we found that complete depolymerization to bisphenol A and dimethyl carbonate was achieved. So our curiosity was the origin of the reactivity. Previously, many reactions, so like as I said, if you put the polycarbonate into methanol, nothing happened. So there could be two possibilities. Maybe we have a high chemical activation energy. So without catalyst or maybe not enough temperature, methanol cannot, just degrade it because of the low reactivity. That's chemical reason. Another reason may be physical issue. Since polycarbonate is immiscible in the system, methanol cannot approach into the polymer at all. So physically blocked. So whatever things you do, the reaction would not be happen. So in the previous, most of the reaction, people utilize the homogeneous conditions, maybe because of that. We want to prove it. So instead of polymer, we adapted the diphenyl carbonate as a model organic system. DPC is soluble in methanol in some slight increased temperature, and at the 100 degree, it becomes completely homogeneous. Interestingly, in case of DPC, you can see gradual decrease is happen, and then depolymerization by the transmethylation methanol. You can see these DMC and then MPC keep forming. That means if we achieve certain homogeneous system, we can continue the depolymerization. So maybe what we need is more physical conditions, physical contact than chemical activation energy. When we apply this DPC in the methanol, nothing, anything, only to mixing it, just grinding it, we receive the complete conversion of the disappearance of the DPC, and then later, complete disappearance of intermediate MPC, and then quantitative production of the DMC. So it's a very, very promising result. So we try this. So what I want to say is, again, previous example, many example, what we do is we adding a the BPA-PC, adding a methanol, and we adding a catalyst to overcome low reactivity, and then we adding solvent to dissolving this BPA-PC and making this methanol and BPA-PC miscible together, make a contact. After the reaction, many papers claim it, they got a very high conversion to BPA in DMC, and they just stopped reporting it. But if you're thinking about their output, you recover bisphenol A, DMC. Usually we adding excess methanol. We have a catalyst. We have solvent. We stop the paper writing here. Usually we do not thinking about their separation process. If you want to go to industry, you need to separating BPA, DMC, methanol, catalyst, solvent, individual. And there will be nightmare to the separation process. So we try to do was minimizing. So by using a bone milling, simply we just adding a bisphenol A, PC, and methanol, and we already observed that if you're making a good physical contact, methanol can break down the polycarbonate. So clearly, when you're mixing these two, even heterogeneous, applying ball milling, this methanol, ball milling maybe can push this methanol molecule into the BPAP system and making a good contact. After hours, we got the complete depolymerization to bisphenol A, DMC, and then excess methanol left. Previously, we have 5 components to separate, but now we have only 3 components. Very, very efficient post-process can be made. So I believe that this is not only about the reactivity, but mechanochemistry can simplify the whole overall process. So we apply this one to the real waste. So the degradation paper, they conduct the reaction with the pure polymers they received from company. And then many times after they got a good data, they are moving to real plastics. But what's the difference between those plastic and then the real plastic is about additives. Those products like safety goggle or compact disc, adding to original polymer, there's a lot of additives like UV stabilizer or thermal stabilizer, many things. Even here, even metals, any things. So if we utilizing catalyst, many times we got a reduction of reactivity because this impurity impact catalyst. But our system, as I mentioned, we didn't use catalyst. That means nothing to effect. Thus, regardless of pellet, safety goggle with some additives, or compact disc of a lot of the side components, we just ball milling with their methanol. We are able to get a high conversion to bisphenol A. I mean, the conversion was a little bit, this is a recovery rate. Conversion was quantitative, but throughout the process, we're losing some. So we got some, slightly lower than 90% recovery rate. But I say their conversion to bisphenol A was very clean. And then this type of chemistry, trans-esterification, transcarbonation, can be applicable to PET polyesters. So plastic cups, which some of them made out of the PET or water bottle, or PLA, we apply the methanol, a little bit different amount. But regardless of their structures, just ball milling grinding, we are able to do a methanolysis, getting a dimethyl terephthalate to 98% or methyl lactate to 82% degradation. So this technology can be applicable to various types of polyesters and polycarbonate. So this is to the end. So thank you for listening. Kind of a long presentation, longer than my expectation, but I want to show that we use a different process other than solution chemistry. And what I claim is, by having a different process, maybe we can increase the efficiency, but at the same time, we're supposed to get distinctive product or unusual reactivity. That's kind of my overall aim of my mechanochemistry research. So I will summarize it in the polymer mechanochemistry from monomer to polymer. The mechanochemistry, I shows that it could be green because of solvent-free. And then we were able to control the molecular weight to the high molecular weight using our LAG selectively. This combination monomer could give us Mechanochemical polymers. And in the final of the chemical degradation recycling, we observed very unusual reactivity of the mechanochemistry. And then we are continue in doing or seeking for the mechano-only chemistry. And then mechanochemistry is not a competition to solution chemistry. It's a kind of complementary method to the solution chemistry, making our realm of synthetic chemistry like a bigger and bigger. So thank you for listening. And then this is my students, current members, and this is the list of alumni who worked under this area. Really appreciate of their devotion, and that is current group members, and that is kind of our recent collaborators in mechanochemistry. Thanks a lot for their intelligent input on this project. And this project has been supported by government at the same time. Samsung, LG made some contribution to this research. And thank you for your attention. And then I would so this is kind of pre-recording, but whenever you have a question, you can directly email me or you can send a comment to CMCC and I will do my best to address all the questions and suggestions you have. And thank you.
Thank you, Dr. Kim, for outstanding presentation, and thank you very much for joining us. Just to remind you all, please email us all your questions to cmccdiscussions@gmail.com. Also, please remember that all of our previous speakers are available to watch anytime on our YouTube channel, and I encourage you to check them out. We also have some great seminar speakers planned in the upcoming months, and we hope that you will join us for all of them. Thank you again.